Okay, good morning. Okay, so let's get started. So the screen on so the projector on the left side seems broken. So actually, it was happening almost every week, but until the last week, I changed the battery and it worked fine. But it seems it's broken. So if there's any way you can switch the input without using this one, so you can do that. But I don't know how. So sorry about that. The one screen is not working. So you can watch this one or through the Zoom. Okay, so let's get started. So sorry about that. So today's main topic is about memory management. So I'm going to spend a fair amount of time talking about this. So somewhat unlike previous weeks, I spent a fair amount of time speaking. But hopefully we have some time for you guys to work on the assignment, PL05 calculator. So before we start, let me speak a little bit about the assignment. So right after the last week's lecture, I released the details of the assignment. So the important thing is that so you are not done just by finishing the coding. So there's something more I'm asking you guys to do. So the details are all details are in this page. So basically, well, just like other exercises, you are supposed to do the coding work. And for this coding work, you are supposed to submit your code through this Jupyter environment. So you have this submit button right next to all the assignment for that matter. But so you are supposed to submit this one. So PL05 calculator. So you don't have to do anything for other exercises. So of course you can do that if you like to. But so the first thing is to submit your code through Jupyter. That's one thing. But other than that, I asked you guys. Sorry, so maybe you should turn off your speaker. Okay, so I asked you guys to get together with other group members and discuss and record what you have been through. So the one important thing is you should find OneDrive folder when you log into your Microsoft 365 account. So in case you don't know how, just check this page. So the first important thing. So go to your Microsoft 365 account and find a folder that looks like this. So the folder's name is programming language group whatever. So your group number. So in case you don't find it, let me know. But so under this folder, you should be able to find these two shared files to which you are supposed to record your activities and summary and reflection. So these things should be done with your group members, so not individually. So you're supposed to do them by a group. And if you open this Excel file, you have actually two sheets. One is called work log and the other is called check. So these are basically for recording your activities. So the important thing is in this Excel sheet, you are supposed to write when you worked, either individually or with other members. I guess it's best to show you what the actual files. Maybe it takes time, so you guys can do it later, and let me know if you have any trouble. And another worksheet, to another worksheet, you are supposed to write what you saw about other group members' work. So, for example, you should be assigned to one of these languages, Go, Julia, or Camel, Rust. And you should see where other members in the group stand in terms of coding. So whether it worked fine or it runs, but it returns some wrong result for some test cases. So the details are again in this spreadsheet. So basically you should write what you witnessed about other members' code. So these are not a great deal of work, so you should be able to finish them quickly as a matter of few minutes. So the main part is this one. So collaborate with other members to write a summary and reflection of this coding work. For example, you're supposed to write how easy or difficult was it to write the calculator using whichever language you are assigned to. And so please discuss with other members how their programs could be improved for clarity, conciseness, and perhaps performance. Performance, that shouldn't matter very much for this exercise, but we'll just discuss the possibilities. And discuss which aspect of each language make the language more productive or less productive. So among others, so please discuss those kind of things and put together them in this summary reflection docx. So these are materials you should submit. So your code, so these are submitted individually. And the other is this summary reflection Word and this Excel sheet recording what you have been, how you have been working on this. Okay, so, and in the end, individual should submit a brief note saying, so you have done all the work. Well, so ITC-LMS, so this should be done through ITC-LMS. Okay, so if there's any question about how you are supposed to submit your work. So your code and Excel sheet and Word document. So these are just put in the Microsoft OneDrive. And at the end, you should submit a small note to ITC-LMS saying you have done. Okay. And it's due May 27th. So any question about this assignment? Okay. So let me get back to what we're gonna do today. So okay, so let me start with this memory management introduction. And at the beginning, I'm going to ask you to take some quiz about memory management. Okay, so memory management. So here's the, so somehow this slide is broken, sorry. So, well, so let me start with something very obvious. So in any programming language or any program for that matter, all values need memory, some memory to hold them. So whether it's integers, floating point numbers, strings, arrays, and structs, for whatever it is, if you want to remember values, you need some memory to hold them. And ideally, programming language manage them on behalf of the programmer. So you don't have to worry too much about where this value should be put and when they should be released or something like that. And different programming languages take different approaches. So the most crude one is sort of manual memory management. Basically, they let programmers manage memory for themselves. So the representative includes C or C++ or some other, languages that tend to be old, like Fortran. So these languages let you perform memory management by yourself. The majority of languages used today, these days, using the approach called garbage collection. And the garbage collection is further divided into two broad categories. One is something called traversing garbage collection, and the other is something called reference counting. So it includes most major languages used these days, including Python, Java, Julia, Go, or Camel. And finally, Rust is taking a somewhat different and interesting approach. So it imposes, so it tries to do memory management on your behalf, but without a garbage collection. So these topics are things that I like to cover in today and the coming few weeks. But before we get started, so let's have some fun. So please take this quiz about memory management, the basics. So you can take the quiz either by following this direct link or go to menti.com and enter this code number 45741905, or by using this QR code. So let me spend some time doing this. So if you follow this link, I'm sorry. So you should be able to see this page. So let me know if it doesn't happen to you. And I'm watching the answer from you guys. So this is obviously a Python program, but many of your answers. So majority of you seem saying, okay, so you should delete this Mimura node, and you should retain the Otake node, this one. So yeah, this is the correct answer. Well, do you know why? Because so this one becomes the return value of this function. So we don't know exactly what happens after foo returns, but well, we should safely assume that this return value is going to be used. So because this one is going to be used, then yeah, you obviously you should retain this node. But what about the other one? So this is created, but after foo returns, there's no way you can use this node, right? So you can safely reclaim it. And also you should reclaim it. Otherwise, you have no chance to reclaim it later. Okay, so I hope that this should be easy. But in case you didn't make a correct answer, my explanation clarifies why. Okay, so let me go on to the next one. I don't know how I can do that. So maybe I switch to the presentation mode and next to the. So I think you should be able to go to the next question. Okay, so this is question number 2. So please start answering. So this time it's slightly different. So before it returns O, it makes it performs another statement. O dot friend equal M. So I'm watching answers coming. Okay, so now, so here's your answer. So this time, I think literally everybody who answered answered it correctly. So except the one. So hopefully my explanation in the previous question clarifies everything. So this time, what's different is that this O dot friend refers to the other node. So even though if you only return single object or Otake, after foo returns, you still are able to use this Mimura node through this field. So you get the return value of foo, and then you reference this Mimura node through O dot friend. So whatever is returned from foo dot friend, right? So you should retain both of these two nodes, right? So this is how it is different from the previous one. And so let's go to the next one. Okay, so again, so click on this, go to slide, and then you get the next question. So again, it's only slightly different. This time, what you do right before returning is M dot friend equal O instead of O dot friend equal M. It's the opposite. Okay, so yeah, somewhat interesting. So, but most of you answered it correctly. So this time, so after foo returned, whoever calls it obtained the reference to this Otake node. But there's no way you can use this Mimura node from the return value, right? So this time you should retain only Otake. So this one is the correct answer. So further question. So the two remaining questions. So this one is somewhat different. So essentially the same question, but I'm asking essentially the same thing in a slightly different way. So you have this function. So you create one node and the second node, and you make the third node and assign to it assign to the same variable you assign to this first node. And unknown code follows. So the question is, at which point this node, Mimura, so the first node you made, can be reclaimed, can be safely reclaimed, when it becomes okay to reclaim or delete this node, the first node you made. Either right after the first line, right after the second line, right after the third line, or somewhere else, which is not shown in the code. Okay. So I guess most of you answered in the way I intended you guys to. So yeah, my intended answer was this C. So right after this assignment, well, especially because there are unknown code that followed. But yeah, so well, actually the answers are more diverse than I thought. And yeah, after thinking twice, yeah, other answers may be legitimate. If you look at the whole code, well, actually, yeah, actually, it's so. First of all, this is what I intended. So at this point, the variable m is still referring to this Mimura node, and which is overwritten by this statement, second assignment that assign another object to the same variable. So at this point, there's no way you can use this node, right? So if you can ever use this node, it should be through this variable m, but m is now referring to another node. So there's no way you can use this node. So this is what I intended. So after this assignment, but if you think more deeply, yeah, it's also legitimate to say, okay, you can actually free this node right at this point, because well, from this program, it's obvious that you are not using this node at all, and after a few lines, you are assigning another node to this m. So yeah, so depending on how you interpret this problem, it's also, strictly speaking, it's also legitimate to say you can free this node right at this point. But You know what I mean, hopefully. So at this point, so the point C, there's no way you can use this node, no matter how you write this unknown piece of code fragment. But anyway, so let me get to the last question. This is the final one. So it's the same, except that you have this O friend equal M right after these two assignments. And the question is the same. So when you can safely this first object you made here. And there are 5 choices, A, B, C, D, or none of them. So you can deduce where you can free it from this code alone. Okay, so answers are somewhat interesting. So this time, the only legitimate answer is the last one. So you cannot deduce from this code alone. So in other words, you cannot delete this node until D. So you cannot delete it even at this point D, because so like I said, you have some unknown piece of code here. So this piece of code may be using O, obviously, and through this O.friend, this piece of code may be using this node again, right? So even if M is no longer referring to this node Mimura, you can still reach this node through O.friend, right? So it is not safe to reclaim this node at any point A, B, C, or D. So the only legitimate answer is none of them, right? So hopefully this quiz turns out to be useful. So useful in the sense that all of them answered immediately the correct answer. So it was worth doing, hopefully. So let me get back to the slides. Where is it? Okay, so so before we move on, so this is the brief explanation or illustration of what I was talking about in quiz particularly 2 and 3. So there's a reference from this O object, so Otake object to Mimura object. So even if the only value directly returned from foo is this Otake one, you can still reach this other node, right? After obtaining the reference to this node, right? So that's the reason why you have to retain both of these two nodes. And what about the the quiz number 3? So that time, the reference was from Mimura to Otake, and the return value was the same, so Otake. So if the caller obtains the reference to this node, you are not able to reach the other one, right? So because the pointer direction is from this one to that one. So if the pointer was the other direction, then you have to retain both, right? So that's the difference between the second one and third one. So somehow the slides are broken. So there was supposed to be some table of contents here, but sorry about that. So from this slide, I start talking about, well, I guess I should have a table of contents. So let me fix that. Okay. So or somehow it still doesn't show up. Okay, now it shows up. Okay, so from this slide, I'm going to start talking about the memory management in C++, or what could go wrong with manual memory management. So this is a quick review of how memory is allocated or managed in C or C++. So you can actually have 3 different kinds of memory depending on it's the lifetimes, so-called lifetimes, the period in which these values behave in a way they are supposed to. What I mean by that is, so first of all, you have something called the global variables or arrays. So these are variables or arrays declared outside any function. So at the top level of your file, just like this. And you have local variables or arrays. These are variables or arrays that are defined or declared inside a function, just like this. And finally, you have a heap, which is in the case of C, allocated by this malloc function. So in the case of C++, it is allocated by a new operator. And depending on how you allocate storage, a memory block, so lifetimes are different. So lifetime refers to the period in which these variables or arrays behave correctly. So behave correctly basically means that when you assign a value and you later retrieve the value, when the variables or arrays remember what you have just put. So in the case of global variables, the lifetime begins when the program starts and ends when the program ends. So basically, the lifetime is infinite. So it lives as long as the program itself. So normally you don't have to care about its lifetime. So you don't have any, so you don't even have a notion of when it dies, because it lives as long as the program itself. But it's different when you are using local variables. So local variables, lifetime starts when a block or a function starts. So this variable or array is allocated when this function foo is called, right? And more importantly, its lifetime ends when the block ends, or in this case, when the function ends. So when a function returns, the lifetime of these variables will also end, which means that if you access these variables after this foo function returns, you are not guaranteed to get what you expect. And in the case of heap, it's totally up to you. So its lifetime obviously begins when you call malloc or new. So when you obtain the return value of malloc or new. And it ends when you free or delete. So it's manual. So it doesn't happen unless you explicitly say, okay, so you are not using this block of memory anymore. So these three types of memory blocks are what C++ or C offers to you. So what could go wrong in this setting? So, or the manual memory management or manual memory management in C or C++. So let's first talk about heap allocated memory. So memory block you allocated via new or malloc. So these blocks must be deleted or freed by yourself at the right spot. But oftentimes the programmer does it wrong. So does it wrong means that the programmer either frees block of memory even if you are going to use it after this, or somehow you forgot to free the memory block at all. The former is something called a premature free. So you use it after you delete or free them, which results in sort of memory corruption. So this memory block, which you thought you are still there, which you thought is still there, is already reclaimed, which means that it may be used by something else, right? And if you, for example, use this block of memory after you in fact free or delete them, then you are going to corrupt the memory, which is using the same block of memory for other purposes. This is the disaster that stems from premature free. And another disaster which may happen is something called memory leak, which happens when you do not delete or free memory blocks that are no longer used. So it doesn't necessarily manifest as a problem immediately, but if you do this for a large chunk of memory and for many blocks of memory, then it eventually results in something called out of memory. So your program is using lots of memory that are in fact not necessary. So this program is almost exactly the same. It's almost a literal translation to C++ of what you have been seeing earlier in the quiz. So you create two nodes and you return one of these two nodes. So this program is wrong because it is leaking the memory of this new node, the first node. So what you should do in this C++ program is to delete M. So you say something like delete M right before this function returns. And so in C++, okay, so this new is using heap allocated memory, right? But another way you can allocate memory is to use so-called stack allocated memory or local variables. So instead of saying new node, you can simply say node. And you can make them non-pointers. Right, so you can still return a pointer to node by saying ampersand O. So this is one of the common mistakes C++ beginners is likely to commit. So like I said, these local variables, so lifetime ends when this function returns. But this program is still trying to use this node after foo gets returned. Of course, well, details depend on what you do after this foo returns. But I think so. Imagine a caller who gets the return value of foo and tries to dereference the return pointer to reach this node. But this node, the lifetime has already ended when the foo returned. So this program may result in memory corruption. This is premature delete. So this is equivalent to prematurely free a block of heap allocated memory when in fact you are going to use it after you freed it. And so this example is somewhat obvious. So from the compiler's perspective, you are trying to return a pointer to a stack allocated memory whose lifetime is going to end when the program returns. So this obvious mistake is likely to be catched by caught by the compiler. So the compiler complains about this program, but it's still not an error. It's just a warning. So this program is somewhat subtler, and the compiler doesn't complain at all, but still it's an error. So this time, because it is obviously an error to return this ampersand O when O is stack allocated memory. So you make this heap allocated memory and return O. But this O object refers to stack allocated another object, this one. So there's some indirection, right? So accessing the return value of foo itself is not error. So it is still safe. But if you traverse this friend field and then try to access the contents of this friend, then it's going to be an error. So it may be referring to the block of memory that may be used for something else already. Or if you are trying to change the content of this O friend, then you may be corrupting the memory block that is used for some other purposes. So this is another way C or C++ programs could go wrong. So the life is C or C++ is that hard, and there are actually tools to make C or C++ programs somewhat safer in terms of memory management. So one often used tool is something called the Valgrind. And the other one is Bohm garbage collection library for C or C++. So this one is particularly useful when you haven't known about it. So you simply replace malloc or new with this garbage collected version of new or malloc, and all the heap memory are automatically collected, just like other programming languages. So I'm going to show a quick demonstration of the library. So this is a simple program that is doing a lot of heap memory allocation. And after you allocated memory, you simply initialize this array somehow. And just so that I'm indicating to the compiler that I'm using this block of memory. And what is happening inside this init array is simply initializing each element with a random number. So it's not anything useful. So if you do that in ordinary C++ program, it's leaking memory. So you are allocating many arrays, and you are not deleting it anywhere. So let me just show what actually happened if you. So each time I'm allocating million elements array, so M is 1 million, and N is 100. Sorry, 1,000. So each time I'm allocating 8 megabytes of array because each element is a double 8 bytes. So 8 by 1,000 by 1,000, it's 8 megabytes. And I'm doing this 1,000 times. So in total, it's going to allocate something like 8 gigabytes of memory. And I'm just trying to show what happens in the memory usage of this program. Sorry. Okay, so this is showing the memory usage of the processes. Oh, sorry. Showing only my program. And let's start this program. Then, so you can see that this program is eating so much memory. So it's currently something like 5-6 gigabytes. And yeah, after a few seconds, it ends. But it's taking something like 8 gigabytes of memory, right? And just increase this to something like 24 gigabytes. So it's supposed to consume something like 24 gigabytes at the end. So something as disastrous as this happens simply when you forget to delete this array, right? And this can be prevented in any garbage collected languages because obviously, well, the only array you should retain on memory is only one array, right? So in each iteration, you allocate this memory, use it, and in the next iteration, you are no longer using the array that was allocated in the previous iteration, right? So you should retain only one single array at a time in this program. And I'm going to demonstrate. So how to prevent this error from happening just by using the garbage collection library. I don't know where the cursor is. Okay, so only thing you have to do is to include this library. And when you allocate this array, you say use GC. So this memory block should be managed by the garbage collector. And you link with this GC library. And watch what happens in this process memory. So this time, yeah, the memory doesn't grow at all, right? So resident memory is something like 27 megabytes. So it doesn't go anywhere close to 24 gigabytes, right? And after a while, it is going to end. So this is what the garbage collection does. So in this case, it's using the garbage collection library for C or C++, but essentially the same thing is happening in any of these languages you are working on. So either Julia, OCaml, and Go. So Rust is somewhat different. So let me get into how this works. So now, so this part is a brief introduction about the garbage collection. So when am I supposed to speak until? So let me check what I said in the beginning. Okay, I said in the beginning, I'm going to speak until something like 11:30 or 40. So yeah, 20 minutes or more. So I'm not going to end the entire topic in this week anyway. So I suspend the talk when the time comes. So yeah, garbage collection. So as you have just witnessed, the fundamental problem of manual memory management, or specifically memory management in C or C++, is the mismatch between the actual lifetime of memory block or objects and the actual period in which your program is accessing them, right? So it is possible that your program accesses an object or a block of memory after its lifetime ended. Just like you are accessing stack allocated object after the function that allocated that stack allocated object returned, right? Or you access a heap allocated object after you free or delete it, right? So this happens, right? Or you somehow forgot to free or delete an object or memory block, despite you no longer access it. So these are both are actually the mismatch between the actual lifetime of the memory block and the period in which you are actually using it, right? So we have to close the gap between the two, right? So the memory block ought to be retained as long as you are going to use it. So garbage collection, well, basically, it is trying to do just that. So I'm going to make it more accurate later, but for now, so what garbage collection is trying to do is to keep objects alive, the memory block alive, or retain memory block, if they could ever be accessed in future and reclaim otherwise. Now, it is essentially doing exactly what we wish them to do. The system automatically does that for you. And the end effect is to eliminate memory leak and memory corruption. So memory corruption happens when you use memory block after you already delete it. Or memory leak happens when you forgot to delete it when you are no longer using it. So garbage collection prevents both from happening. So the essential question is, how does the system know which objects may be accessed in future? The system somehow has to know it, right? When the system tries to make this happen. So this is the fundamental question we have to think about. So before getting into what the garbage collector is actually doing, let me just note that the precise judgment is undecidable. So it's something impossible to know. So I'm showing a trivial example to illustrate this point. So imagine that you are actually so right before executing this second line of this program. So right before this if expression, if statement, and ask if the object or the memory block pointed to by this P pointer should be detained or not at this point. So right before you are executing the second line. So we are essentially asking if this expression is going to be evaluated before executing this second line. Well, this question is obviously equivalent to ask if the return value of f of x is 0 or not. So if f of x returns 0, then p is going to be used. But otherwise, it's not going to be used, right? And well, again, so we are asked to judge if P is going to be used or not right before executing this second line. So we are essentially asked to decide if f of x is going to return 0 or not without actually executing f of x. So this is actually an undecidable problem, where if you have learned something about undecidable problem. So given a function description, even if you know the program body of the function, deciding if f of x ever terminates is undecidable. So this is a very fundamental theorem in the computer science you should have learned about. So if f of x doesn't terminate, then p of the pointer p is not going to be used, right? So judging if f of x ever returns 0 well contains as a subproblem deciding if f of x is going to terminate, which is undecidable. So the point is somewhat trivial and only of a somewhat theoretical interest. But I'm just making a point that we cannot precisely judge if a particular memory block is going to be used or not 100% accurately. So the only result is to somehow conservatively estimate objects that may be accessed in future, which means that it should never happen that we somehow reclaim objects that are in fact are going to be accessed in future. But we accept that we reclaim those that are in fact never going to be accessed. So in this particular case, we say it's okay to retain the memory block referenced by this pointer p, even if f of x may return 1 or non-zero value. I hope that I think that you will think this is a reasonable compromise, right? So this is just a small theoretical note about what we are actually trying to do actually. Given that it is impossible to 100% accurately determine if a particular memory block is going to be used or not. And then, so that the question now becomes an easier question, how we can estimate objects that may be accessed, given that it is okay to say this object may be accessed, even if it may in fact not. So this answer is, so one reasonable answer we can make relatively easy. So one is, so first of all global variables may be used no matter what the actual program is doing, because global variables are always there, right? So no matter which part of the program you are executing, you can always refer to global variables, right? So whether the program actually does this is subject to the program. So it depends on the program. So by carefully looking at the program, you may be able to decide, okay, this global variable is no longer used by this program, but we ignore these details. So we simply assume that all the global variables may be used in future. In addition to global variables, we also assume that all local variables of currently active function calls. Active function calls are function calls that have started already but have not finished yet. So all local variables of active function calls are assumed to be maybe used. So let's consider this program. So you have two global variables, S and T. So no matter where you are, no matter what the actual programs looks like, we always assume that S and T may be used. And as a result, all the memory blocks referenced by S and T may be used in future. And also suppose that, so we are executing this program and main is calling F, which is calling G, which is calling H, and we are now in the beginning of this H function, which is illustrated like this. So main is calling F. All local variables of currently executing HGF and main may be accessed in future. So more specifically, P may be used in future, Q may be used in future, and R may be used in so I'm now back and I need to restore the screen sharing. I don't know how long it was happening. Hopefully it's not that long. Okay, so let me continue. So these are just fairly simple and conservative estimation about which variables may be used in future. And more importantly, all the objects that are reachable from them by traversing pointers may also be used. So this is a point I made in these quizzes in the beginning, right? So if P is a pointer, P may be used, and this X field may be used. So first of all, because P may be used, the memory block referenced by P may be used, right? And because P arrow X is used, the memory block referenced by this P arrow X may also be used, right? So this object may also be used. And transitively, memory block that is referenced by this object may also be used, right? So the net result is we are going to assume that objects that are reachable from global variables and local variables by traversing pointers are all objects that may be used in future. This is basically how the garbage collector determines if some memory blocks or objects may be used in future. So this is a very simple criteria that can be judged without looking at the program at all. So without looking at the piece of code, the actual piece of code. Simply this variable is there, then memory blocks may be used. And simply because this memory block may be used, all the memory blocks that are referenced from this memory block may also be used in future. So something as simple as this. So I'm going to get somewhat into it in the rest of this slide and coming weeks. But I guess it's almost time to finish my part. But just a few terminology notes that are often used in the context of garbage collection. I'm already saying this terminology many times, and an object. So in the garbage collection literature, when we say an object, simply to mean the unit of memory allocation. So it may not be exactly an object in terms of in the context of object-oriented programming language. It is equivalent to just a memory block, the unit of memory allocation. So in the context of C, it is simply a memory block allocated by a single called malloc. Or in C++, it is a memory block allocated by new. So those are all called objects in the garbage collection literature. I already spoke about this too, but the loot is another very commonly used term in the garbage collection. So the loot generally refers to objects or the block of memory that are accessible without traversing any pointers at all. So the loots are objects that are accessible by default or by construction. The obviously accessible objects, such as global variables or local variables of active function calls. So this is basically where all the reference to the objects are sort of started or rooted. So another commonly used terminology is reachable objects. So this refers to objects that are reachable from the root by traversing pointers. So we also use live or dead objects. So objects that may be accessed in future are called live objects. So this object is still alive. So in other words, live objects are objects that should be retained and that may be used in future by the program. And the opposite term is obviously a dead objects. Dead objects are objects that are never going to be used in future. And we say that we call dead objects simply garbage. So garbage that should be or can be collected or reclaimed. So we often call the program that is doing the garbage collection collector. Well, it's simply a short term of the garbage collector. And this is somewhat a strange terminology. So in the garbage collection literature, we often call the user program the mutator. So we simply call the user program. So we can simply call it the user program all the time, but somehow, for some reason, in the garbage collection literature, we call the user program the mutator. Whether the mutator basically means somebody who is mutating the data structure. So this is very sort of garbage collector centric viewpoint. So in this viewpoint, the garbage collector is a program that is doing the real work, when in fact it is the opposite. What is doing the real work is obviously user program. But when we talk about the garbage collector, so garbage collector is the guy who is doing the real work. And the user program is simply a program that is mutating whatever data structure the garbage collector is working on. So that's why this is called a mutator. So again, this is a very garbage collector centric terminology. So it is viewing the program and the user program as someone simply mutating objects, mutating the memory that the garbage collector is working on. So with these terminologies, so the basic principle of the garbage collector is objects unreachable from the root are dead, so should be reclaimed. So the way the garbage collector basically works is somehow to identify all the objects reachable from the root, to identify all the objects that are not reachable from the root, and reclaim all these objects. So that's the way the garbage collector basically works. And I guess I'm going into further details in the next week. And with that, I want to finish my part speaking. I leave the remaining time for your exercise. And the way, so if there is any question so far, I take the question at this point. Okay, so the way you're supposed to work is again, is details in this page. And of course, depending on where you are, so maybe you are still working on individual coding, but nevertheless, so please get together with other group members, just like the last week. I'm going to make a Zoom breakout room. So this time I made a mistake in the last week. So this week I make the breakout room so that you can choose the room you enter. So please enter the room, Zoom breakout room with the same number with your group number, so that everybody in the same group can meet. Of course, if everybody is in classroom, you don't have to use Zoom at all. And again, I forgot to mention in the beginning. So in this Google Sheet, so you have another tab for today. And just like the last week, please color yourself, indicating where you are. So if you are in the classroom, you mark yourself with yellow. And if you are home, then you make it cyan, so that all the group members know where you are. And if all the members are in the classroom, then you physically get together. And if all the members are home, just enter the Zoom breakout. And if some of the members are in the classroom and some other members are home, it's slightly complicated, but so everybody should enter the Zoom breakout. And actually, you can use the other room over there. So especially when you have to talk to somebody working in home, and then maybe it's better to go over there, which tends to be somewhat sparser compared to this room. So, okay, start coloring this spreadsheet and get together with other members and start working on it. Oops. So, okay, I'm going to make a breakout room. So I've just made 13 breakout rooms and opened it. So I guess you can join any room you want, but you are supposed to enter the room with the same group number of your group number. So like I said, the other room is completely empty. So if you want to talk to each other, well, actually, you can use the other room. So maybe better, much better than this room.